A small piece of uranium, no bigger than a grape, can generate enough electricity to power an entire neighborhood for a year. But how is that even possible? How can something so small hold so much power? To find out, we need to visit the mines, factories, and nuclear power plants responsible for producing and processing the most dangerous metal on Earth. This is the story of enriched uranium and how it became the key to powering our world. The story of uranium begins in 1896. That's when French physicist Henri Becquerel discovered something strange. He noticed that uranium could emit energy all by itself, without being heated or exposed to sunlight. This phenomenon became known as radioactivity. Inspired by this, Marie and Pierre Curie discovered other radioactive elements like radium and polonium, pushing the science even further. In 1932, British physicist James Chadwick discovered the neutron, a tiny neutral particle found in the atom. And just 6 years later, German scientists Otto Hahn and Fritz Strassmann, with help from Lise Meitner and Otto Frisch, discovered that uranium atoms could actually be split in two by neutrons. This process is called nuclear fission, and it releases an enormous amount of energy.
But there was a problem. Natural uranium is made up of about 99.3% uranium-238, which is not very good for fission. Only 0.7% is uranium-235, which is the part we actually need. So scientists needed to find a way to increase the amount of uranium-235. This process is called enrichment. During World War II, enrichment was one of the key goals of the Manhattan Project, the top-secret program that built the world's first nuclear bomb. Back then, scientists used methods like gaseous diffusion and electromagnetic separation to enrich uranium, but these methods were slow and used huge amounts of electricity. Everything changed in the 1950s with the invention of the gas centrifuge. This high-speed machine spins uranium gas at incredible speeds, separating the heavier uranium-238 from the lighter uranium-235. Gas centrifuges are still used today and are far more efficient. In 1951, the first usable nuclear electricity lit 4 light bulbs at the experimental breeder reactor in Idaho. Just a few years later, in 1954, the Soviet Union connected the world's first nuclear power plant to the grid. Today, enriched uranium powers about 10% of the world's electricity. Everything changed in the 1950s with the invention of the gas centrifuge. This high-speed machine spins uranium gas at incredible speeds, separating the heavier uranium-238 from the lighter uranium-235. Gas centrifuges are still used today and are far more efficient. In 1951, the first usable nuclear electricity lit 4 light bulbs at the experimental breeder reactor in Idaho. Just a few years later, in 1954, the Soviet Union connected the world's first nuclear power plant to the grid. Today, enriched uranium powers about 10% of the world's electricity. So, where does uranium come from? Most of it is mined in remote regions like the deserts of Australia, the plains of Kazakhstan, and the rocky landscapes of Canada. These 3 countries produce around 70% of the world's uranium. Uranium is found in rocks like uraninite, often in very low concentrations, sometimes less than 1%. Mining can be done using massive open-pit methods or through deep underground tunnels. In some places, a special method called in situ leaching is used, where chemicals are pumped underground to dissolve the uranium and bring it to the surface. Once mined, the uranium ore is sent to a processing plant. There, it's crushed into fine particles and mixed with chemicals to separate the uranium. What comes out is a bright yellow powder known as yellowcake or uranium oxide. It contains about 80% pure uranium. Yellowcake is not highly radioactive, but it still requires protective clothing and careful handling. 1 ton of yellowcake can generate as much energy as several million tons of coal. Next, the yellowcake is sent to a conversion plant, where it is turned into uranium hexafluoride, a compound that becomes a gas at just 56 degrees Celsius. This gas is perfect for enrichment. The uranium is first purified to remove other metals and impurities. Then it is mixed with hydrofluoric acid and heated, forming uranium hexafluoride gas. Because this gas is corrosive and dangerous, it is stored in special steel containers and handled with extreme caution. Inside some of the most secure facilities in the world, the uranium hexafluoride gas is pumped into gas centrifuges. Tall, narrow machines spinning at over 50,000 revolutions per minute. At this speed, the lighter uranium-235 moves toward the center, while the heavier uranium-238 moves to the outer edge. The gas centrifuges are arranged in long series called cascades, sometimes made up of hundreds or thousands of machines working together. They run non-stop, quietly humming as they separate the two uranium types. The enriched uranium-235 is collected and turned into a fine powder called uranium oxide. This powder is then compressed into small cylindrical pellets, each about the size of a coin and weighing just 7 grams. Each of these pellets holds as much energy as a ton of coal. The pellets are then baked at 1400 degrees Celsius, making them strong and stable. They are checked with lasers, X-rays, and scanners to make sure they are perfect. Next, the pellets are loaded into zirconium tubes, a metal that can handle heat and radiation without absorbing neutrons. Each fuel rod contains about 400 pellets. These rods are bundled together into fuel assemblies, with each assembly weighing around 500 kilograms and containing over 100,000 individual welds. Each fuel assembly is tested for strength, purity, and exact weight. It will eventually be used to power hundreds of homes for a year. At the nuclear power plant, the assemblies are loaded into the reactor core, the heart of the plant. A typical reactor holds over 5,000 fuel rods. Inside the core, neutrons hit uranium-235 atoms, causing them to split and release energy. This starts a chain reaction that keeps going as long as it's controlled. The heat from the reaction is used to boil water, which creates steam. The steam spins massive turbines, which generate electricity. Each nuclear reactor can produce more than 750 megawatts of electricity, enough to power 500,000 homes. And unlike coal or gas plants, nuclear reactors don't produce carbon emissions. After about a year, the fuel rods are removed. They are still hot and radioactive, so they are placed into deep cooling pools filled with crystal clear water. These pools cool the rods and block radiation. Sometimes a soft blue glow appears in the water. This is called Cherenkov radiation, caused by particles moving faster than light does in water. It looks like science fiction, but it's completely real and harmless when contained. The rods stay in these pools for at least 10 years. After that, they are moved to dry storage containers made from concrete and steel. These containers are designed to last for decades, even centuries, and are kept in special storage areas. Scientists are also working on long-term solutions like deep underground repositories. These are located hundreds of meters below the surface in stable rock formations and are built to hold waste safely for thousands of years. Despite the myths and fears, modern nuclear power is safe, clean, and reliable. It produces a small amount of waste compared to fossil fuels and offers a powerful solution to the world's energy needs. And all of it, every spark of light, every watt of electricity, begins with a tiny uranium pellet. So the next time you flip on a light switch, remember, somewhere out there, a piece of uranium, smaller than a grape, might be making it happen. Thanks for watching. If you enjoyed this video, give it a like and subscribe for more.